Let's talk about something huge. And I mean literally huge. Our planet's oceans. They are absolutely vital to our existence, and yet they are almost a complete mystery. We actually have better maps of the surface of Mars than we do of our own seafloor. So today, we're going to dive into the massive challenge of mapping America's underwater world and how a really simple, elegant idea in data management could change everything.
So here's the big question, right? How do you possibly map the 90% of our oceans that are just hidden? How do you turn this endless, churning sea of information into one single, trustworthy map? And this isn't just some academic thought experiment. The answer to this affects the safety of the ships carrying goods around the world, our ability to forecast tsunamis, and how we prepare for rising sea levels.
All right, so meet the heroes of our story. The group taking on this absolutely monumental task is NOAA's National Bathymetric Source Program, or NBS for short. Now, bathymetric is just a fancy science word for water depth. So their mission, simply put, is to create and maintain the one single authoritative map of the entire American seafloor. It's meant to be the final word, the official atlas, for everything that happens underwater. So why should we care so much about this one map? Well, it's a really big deal. This is the data that keeps giant container ships from running aground. It's what we feed into our most advanced computer models to predict coastal flooding from hurricanes. It helps scientists protect fragile coral reefs and other habitats, and it even helps us figure out the best places to build things like offshore wind farms. This isn't just a map. It's a critical piece of our national infrastructure.
Okay, so the mission is clear, but here's the catch. Here's where it gets really, really hard. To build that ultimate map, you first have to solve a data problem of truly epic proportions. It's not just about collecting the data. It's about trying to manage a literal sea of it that's flowing in constantly from hundreds of different sources all the time.
To try and tame this data flood, the NBS uses a four-step workflow. First, they have to acquire data from anywhere and everywhere they can get their hands on it. Then comes the really heavy lifting. They have to normalize it. That's a huge job of getting every piece of data into a standard format with a standard quality score. Next, they compile it. This means for any single point on the map, they might have a dozen different depth readings, and they have to figure out which one is the best, the most reliable one. And then finally, they extract that clean, compiled data to create specialized products for everybody from ship captains to climate scientists. And let me tell you, this process is a true data gauntlet. I mean, just imagine for a second. You're trying to manage wildly different data formats coming at you. You're getting constant, tiny little updates and corrections that you have to track. You have to be able to prove with 100% certainty where every single data point came from. And to make it even more fun, they have to sort all this data into different buckets, like qualified data, unqualified, sensitive, and each bucket has its own set of rules. It is, as you can imagine, massively complex. So all of that complexity just screams out for a better way to do things, right? And that brings us to our solution, a new and refreshingly simple idea called the simple lakehouse.
You know, this quote from Professor Hannes Müller-Reyssen, who co-created DuckDB, just hits the nail on the head. He's pointing out how absurd a lot of modern data systems have become. The whole point of these data lakehouses was to store huge files without needing a traditional database. But they got so complex that you ended up needing a database just to manage the complexity. It totally defeated the purpose. He's basically saying, this makes no sense.
So here's the difference, and it is night and day. On the left, you've got the old, complex way, what's been called a zoo of tiny files. It's just layers upon layers of metadata and manifests just to figure out where your actual data is. On the right, you've got the Duck Lake idea. It is so simple, it's brilliant. Use a reliable database for what it's good at, keeping track of your data's location and version. And then put the actual massive data files in cheap, simple cloud storage. That's it. Problem solved.
So what is Duck Lake, really? Well, don't think of it as a single product you go out and buy. It's more like a recipe, an architectural standard. It basically says use a rock-solid open-source database like PostgreSQL to be your librarian, to handle the what and the where of your data. And then let the actual books, the really heavy data files, live as simple files in what's called object storage,
like Amazon S3.
So, you've got this huge, messy, complex problem from the National Bathymetric source. And you've got this incredibly simple, powerful idea with Duck Lake. What happens when you put them together? Well, as it turns out, it's a perfect partnership. Just look at how neatly this architecture solves the NBS's biggest headaches one by one. They've got all those frequent small data updates. There's a feature called inlining that buffers those changes perfectly. They need 100% reproducibility for the science. Bam! Time travel lets a scientist query the map exactly as it existed on any given date in the past. They need to secure sensitive data. It has built-in encryption. It's almost like it was designed specifically to solve these exact problems.
And you might be wondering, okay, that sounds cool, but can it handle the scale? You bet. This architecture isn't just a theory on a whiteboard. It's been tested managing a petabyte of data. That's 1,000,000 gigabytes, spread across hundreds of millions of updates. It is more than ready for the kind of scale the NBS is working at.
And all that simplicity we've been talking about, it translates directly into speed. By getting rid of all those confusing middle layers, the time it takes just to plan a query, to figure out which data files you even need to look at, completely collapses. Instead of taking hours, it takes seconds. You just ask the database. It tells you exactly where to go, and you get your data fast.
So what would this all actually look like in practice for the NBS? Let's take a look at the blueprint for a system that's ready for the future.
Here it is. This is the blueprint. It's modern, it's flexible, and it's cloud native. And what's really cool is how it evolves with the NBS is already moving toward. The data files themselves live on AWS S3. The card catalog is a PostgreSQL database. Duck Lake is the intelligent glue that connects them. All the number crunching is done in Python, which the team already knows, and everything runs in scalable containers using Podman. It's a natural next step. Now, I know these diagrams can look a little intense, but don't worry about reading every box. The key takeaway is this. All those complicated steps we talked about earlier, acquire, normalize, and compile, are now handled by automated scripts. They just talk to the Duck Lake system, which tells them exactly which raw data files to grab from storage, they do their processing, and then they save the results as new, perfectly versioned files, with the database keeping track of every single change.
And the same beautiful simplicity applies at the end of the line, in the extract phase. When an application needs a specific map, maybe for a ship's navigation system or for a scientific model, it just asks the Duck Lake system. It gets pointed directly to the exact, correct, final data it needs. The end result is the same high-quality map, but the process of getting there is just way faster, simpler, and more reliable.
But what's really profound about this entire approach is how it flips the whole philosophy of data architecture completely on its head.
The old way was like a fortress. You had this giant central data warehouse sitting at the top like a king on a throne, dictating all access. If your application needed data, it had to go through the main gate and ask permission. The new way flips that entirely. It empowers the client. Any application, any scientist can now talk directly to the metadata catalog and the data storage itself, pulling exactly what it needs when it needs it. It is a fundamental shift from top-down control to user empowerment.
And this is really the ultimate goal. As Professor Muleisen puts it, it's about moving away from a world where people, even brilliant scientists, actually fear massive data sets because they're so hard to work with, and moving into a new world of confidence where that data becomes an accessible, powerful tool that you can actually use to make discoveries.
And that really leaves us with a final provocative thought. Mapping our oceans is just one massive scientific challenge. How many others are out there, in genomics, in astronomy, in climate science, that could be cracked wide open? Not by collecting more data, but by adopting simpler, more elegant ways to make the mountains of data we already have finally easy to use. What else could we discover?